Okay, so today we're going to talk about conservation of momentum versus conservation of energy. In the sense that sometimes, often you see problems on my tests or on your problem sets or on the AP, and you're not sure what to use. Okay, so obviously there are a lot more things you could use besides these two equations, the conservation of momentum equation and the conservation of energy equation, but today I'm going to focus on how you could distinguish between the two. And I'm doing this because on the last test, some people kind of mixed up which one to use when. Okay, so conservation of momentum, we've talked about this a little bit for the last 2 days. It's true when you have no net outside forces on your system. That's going to be true a lot of the time. It's true for a lot of single objects, like that paper clip sitting on my desk over there, or these books. But if they're not moving, or if it's just one object moving, using conservation of momentum isn't going to be terribly useful. So it's useful when you have more than one object colliding and there's no outside force, and you know at least some of the velocities, whether they be initial velocities or final velocities. Okay, conservation of energy on the other hand. So we have the energy at the beginning, and this is the three types of energy that go into this equation are K, or kinetic energy. And the equation for kinetic energy is 1/2 mv squared. Okay, plus our potential energy, mgh0, plus our spring potential energy, and this is all initial, is equal to all of those things at the end. Oh, I shouldn't have put a knot there. And this is true, so you can't always use this equation. This equation is true when there is no heat and no work. Okay? So that's when this is true. Okay. This is useful in situations. It's technically still true for more than one object. So if you had two objects and they collided and no energy was lost to heat because it was a completely elastic collision, this would still be true. But usually 99% of the time when you use it, you're only dealing with one object. And when I say that, I don't mean there is only one object in the problem. I mean, like, in the time frame the question is asking about, you're only dealing with one object. Okay? So, for example, and I'm going to give you an example of when you could use both. Say you have a ball sitting on the top of a hill, and a different ball sitting on the bottom of a hill. Okay, and this ball rolls down, and eventually it's going to hit the other blue ball. Now, conservation of energy is going to be useful up until the very moment before they hit. Useful before the collision. Okay, conservation of momentum is useful, assuming this is a flat surface and not still on a curve or hill, is useful for right before they hit, like the instant before they hit, and after they have collided. So maybe this white ball is bouncing back and the blue ball is going forward. Okay, so that's an example of a situation where conservation of energy is useful for one part and conservation of momentum is useful for another part. What I would like you to do is actually take out your packet and turn to page 20. Okay, and what I want you to do as you watch this video is to answer the questions in the Google form. So I'm going to talk you through this problem. We're not going to actually do the problem out, but I'm going to talk you through which concepts apply to which parts, but I'm going to give you kind of a little bit of time to think about it, and you can even pause the YouTube video if you need to figure out, to think about it for yourself. Okay, so we have this kind of weird setup. We have a block and it is on a frictionless tabletop and it's placed up against the spring, and the spring is attached to the wall. So the block is pushes the spring inwards, and then basically when the spring lets go, the block is going to go forward and shoot off of the table. Okay, so you might think, okay, well, right here I have two objects. I have a spring and a block. Here's the only problem. It says that the spring has negligible mass. So when it says that something has negligible mass, you're kind of not counting it as an object. Okay? So what that means is actually throughout all of the process, actually the entire process, energy is going to be conserved. Okay, so part A says calculate the time elapsed from the instant block A leaves the table to the instant it strikes the floor. And I know we were talking about conservation of energy and conservation of momentum, but I just want you to take a minute and write down in your form what concept you think you use for that. Okay, so take about 15 seconds. Pause the video. Okay, so here's the deal. We're looking for time. And it would be nice to use conservation of energy or conservation of momentum. I mean, momentum is not conserved. And momentum is not conserved because gravity is acting on this guy. But even though energy is conserved, there's no energy, or there's no time in the energy equation. Okay, what that tells me is I probably have to use kinematics. Okay, and I probably have to use these heights that it gave me over here to calculate the time. Okay, part B asks me to calculate the speed of the block as it leaves the table. Okay, and I want you to look at the numbers that are given to you and think about how you could calculate the speed of that block. Okay, so You can pause it if you need to, but basically you have to look at what you have. Okay, so there are two viable options depending on what information you have. Okay, so say we knew everything about this spring. Okay, we know that energy is conserved this whole time. So we could say, I can calculate the energy here, and I can calculate the energy right here before it leaves the table. And those should be the same, and I should have the speed of the block. And that would be great. But to calculate the energy here, okay, there's gravitational potential energy. I can calculate that because I have the height. There is spring potential energy, and that is 1/2 k delta x squared. I can't calculate that because I don't know how far back the spring is compressed. So I don't know this x, or in our equation delta x. Okay, that tells me I can't use energy. The other thing I can do, looking at the information given to me, is once again, I can use kinematics. Okay, I know how long it's in the air. I know that it went a distance of 1.2 meters, so I know I can use kinematics. Okay, for C, it says calculate the distance the spring was compressed. Take a minute and decide how you're going to do that. Okay, so once again, I could use kinematics to find this last part, but if I want to know about the distance the spring was compressed, if I'm dealing with springs, I basically have to use force or conservation of energy. Okay, I don't know anything about the force used to push the spring back. Okay, but I do know energy is conserved. And I know that energy right here, where the spring was pushed back, has to be equal to energy at the edge of the table. I know the spring constant K, and I know how fast this was going at the edge of the table. So I'm actually going to use conservation of energy for this one. So sigma E naught equals sigma E. And for that, I'm putting in, it has no kinetic energy at the beginning. It has gravitational, and it has spring potential, US naught. Okay, and at the end, there is kinetic energy. There's still gravitational, but it's actually going to be the same because it didn't move up or down. So I could set my 0 as the height of the table and say both of those are 0. And I have no spring potential because the spring is no longer squished. Okay. The second part, which is actually on page 19 because I stapled these backwards together, is you have another block and it's placed at the edge of the table. Okay, the spring is compressed back again and it says X, so I think that's probably the same distance. And as it gets to the end of the table, it collides with the other block. Okay, so if I flip the page, I can see the diagram for that. Okay, so in part D, it says if you got the same answer for X, or if X was the same as it was from before, how far are these two blocks going to travel? And if you look at this picture, it shows them drawn together.